So we're getting towards the end here, okay, of this unit. Okay. So we're going to be doing kind of the last topic here. Okay? And the last topic is projectile motion. Projectile motion ties together everything we've done in this unit with the exception of gravity. Okay, put 2 please up. Okay, so a projectile, very simply, put 2. Okay, a projectile is any object that's essentially flying through the air, but is not powered. Okay, so a plane is not a projectile. Okay, a rocket is not a projectile. Anything that can power its flight is not a projectile. Okay, but if you throw a ball or a rock or you like hit a golf ball, okay, any of those kind of things that are not powered, okay, they follow the same path, okay, or a similar path through the Earth's gravitational field. Okay, so for example, if I was standing on the edge of a cliff, okay, and I threw a rock, okay, off the cliff, okay, the rock would do this. Okay, it would follow an arc down to the ground. Okay, and the reason that this is an arc is because at first, the only movement of the rock is due to me throwing it. Okay, so if I just throw it like perfectly horizontal, okay, it starts out pretty horizontal, and most of its motion is horizontal. But as soon as it leaves my hand, what's pulling it? Gravity. Okay, and gravity is going to not just pull it, it's going to accelerate it. Okay, so this object is going to travel horizontally due to my throwing it. But while it's traveling horizontally, it's going to start going faster and faster vertically as well. These two things are occurring simultaneously. Just like when a boat is being rowed across a river. Okay? It's going both across the river and down the river at the same time. Okay? The difference here is one of those two components is accelerated motion due to gravity. Okay? Which is why when something goes off of a cliff, its motion becomes vertically dominated very quickly. Okay? I mean, no matter how fast you throw something or for some reason ran off of this, okay? It doesn't matter how fast you're going, that horizontal part is not going to change. There's nothing to speed you up or slow you down horizontally. But gravity is going to speed you up vertically, okay, the entire time until you hit the bottom. Okay? Everybody follow me on that? Okay? Because I mean, I'm sure you've all seen, you know, like movies where a car goes off a cliff. Right? It's this like staple of old movies. Okay, car drives off a cliff. Well, it starts out like this and then very quickly arcs down to the ground, unless you're watching Looney Tunes, okay, because Wile E. Coyote can run off a cliff but doesn't fall until someone points out to him that he's no longer standing on the cliff. Okay, that's a little artificial. Okay, but most things arc down to the ground very quickly. Okay, like has anyone seen the movie Thelma and Louise? Okay, don't. If you haven't seen it, it's 2 hours of your life you'll never get back. Okay? And I hate Susan Sarandon. Her voice just grates on me. Okay? At the end of the movie, spoiler, okay, at the end of the movie, they drive their car off a cliff. I was the only person in the theater who cheered. I got a lot of dirty looks. No, but yeah, at the end of the movie, they drive this car off the cliff. And they actually, to film it, actually did drive a car remotely off of a cliff. And it becomes, like, it starts out and it just looks like it's hanging there. Okay, it looks like it's literally driven right off the cliff and it almost has wings. Okay, but it only looks that way because from the perspective of the shot, you can't see that it's starting to move vertically yet. Okay, the shot is just done so that it's supposed to create, I guess, a feeling of nostalgia or something for these people. Anyway, okay, you don't see it at first. Okay, and that's because the vertical part hasn't become the dominant part, but very quickly it does. Okay, and then the front end of the car goes down and plummets down to the ground. Okay, everyone okay with that? So in most of the projectile motion we're going to look at, it's going to be two-dimensional. There'll be a horizontal component and there'll be a vertical component. Okay, the horizontal component will be an object moving at a constant velocity because there won't be anything to speed it up or slow it down. but the vertical component will be accelerated motion. Now, the simplest projectile is just a falling object, okay? It hasn't been thrown horizontally, it's just been dropped. That's the simplest projectile, okay? It falls due to gravity at 9.81 meters per second.
If you drove, well, not that I plan to, but if you drove a car off a cliff,
I'm glad you qualified that.
would it eventually like get to the point where it would fall like just vertically?
In the real world, there would probably come a point where it would be almost entirely vertical because of air resistance, okay? It's still always going to have some small amount of horizontal component because even air resistance is not going to completely kill your forward momentum, okay, the velocity you have forward. But your vertical motion becomes so much greater than anything you could have imparted to it before that horizontally that it looks like it's, okay. But if you actually examine the crater of anything that would do that, it's always going to have an angle to it, right? Because it's going to be doing both at the same time. Okay? That's why most often, if you look closely at meteor craters, okay, they almost always have one side that's kind of open, okay, and one side that's kind of dug in, and that's because meteors very rarely come straight down and hit the object that they hit. Okay, they usually come in at an angle, right? Like how many people saw the fireball the other night? You guys didn't see that? I didn't see it either, but I saw it on the news. Okay, there was a giant fireball, okay, that flew over us, okay, a piece of comet, okay, that encountered the Earth's atmosphere, right? But it doesn't come like this, like straight at you. It streaks across the sky because it's a projectile, okay? When a meteor or a comet encounters the Earth, it almost never goes like this, okay? Because the Earth is moving, the meteor is moving, okay? So it's always going to be a bit of a glancing blow, okay? In fact, if you look now at the aerial footage they had of the lander, the Perseverance lander, you can see that that crater is shaped kind of like this, okay? This is the hard rim, okay, on this side of the crater, and this side of the crater is softer because the meteor came in like this, okay? And so it struck, but it was moving a bit horizontally when it did so. All right, is that making some sense? All right, so projectile motion is something that we see a lot, especially in movies, okay? It's used oftentimes because there's this natural fear of falling. Okay, there's this natural fear of that, okay, evolved fear of that for us. And so it's something that conjures up an emotional reaction. It can also be used, okay, to create a sense of speed, right? And nobody harnessed this better than Lexus. Lexus had this ad campaign back in the late 90s for their IS 300 sports sedan, okay? Their advertising campaign was, our car is faster than gravity. People are like, ooh, that's impressive. Gravity's fast. I don't like falling, right? If I fall, I accelerate. People understand this. This is like a visceral thing that we understand. So they said, our car is faster than gravity. And they built their advertisement around it. Okay? This is what they did. They had a car on the ground racing on a runway, like an airport runway or a tarmac, towards an X. They took another Lexus and suspended it from a helicopter directly above the X. And they raced to get to the X first. Okay? They dropped the car from the helicopter, and the car on the ground tried to beat it to the X. Now, if you watch the ad carefully, you see the flaws in what they did, but of course they don't point these things out. They're there so that, you know, they're not like legally liable, but the ad looks incredibly impressive, because to think that a car on the ground could beat a falling car to a spot is impressive, because it shouldn't be able to do that. Okay? No car on Earth can accelerate at 9.81 meters per second squared unless it's dropped from a helicopter. Okay? That's the only way to do that. But what we have to remember is, first off, this is the real world. Eventually, all falling objects hit what? Not the ground. Terminal velocity. Nothing falls through the Earth's atmosphere at 9.81 meters per second squared for very long. okay? Because as it falls, air resistance builds up. The faster you go, the greater the force of air resistance until you hit terminal velocity. That means you no longer accelerate. You reach a maximum falling speed. It's still enough to flatten you, believe me, okay? But you won't ever fall any faster than terminal velocity, which is variable. It depends on your shape and air pressure and temperature and all that kind of stuff, okay? Which is why if you ever watch like the skydivers, okay, if they want to go slower, they like spread eagle. Okay, if they want to fall faster, they kind of pull in like this, and it decreases the amount of friction or air resistance they experience. So a falling car is only going to hit a maximum falling speed. A car on the ground can go faster than that. Why?
This is maximum speed is every 10 units.
Yeah, it's powered. Okay? And a car on the ground it doesn't fall. A car on the ground travels in its most aerodynamic dimension. The falling car is going to fall flat. That's its least aerodynamic dimension. Okay? And then on top of it all, something they never show you but is actually happening. The car on the ground gets a head start. Okay? The car on the ground doesn't start from rest like the falling car does. Okay? They trigger the falling car when the car on the ground hits this spot, so that they're equidistant. They each travel the same distance to the spot. Okay? But the car on the ground is at its maximum speed, which for the Lexus was considerable. Okay? It was a very fast sports sedan. Okay? But it's already traveling at its maximum speed. This object has to accelerate. So you just have to do the calculations. You just have to set it up so that this distance can be covered in less time than this distance. It's easy math. Okay? But you make it look terribly impressive. I'm going to show you the ad here in a minute. Okay? But you make it look terribly impressive.
So they use like a whole actual car,
Yes.
so they just wasted it.
Yes. Yeah. Okay. And then Mythbusters did a thing. I'll show you the Mythbusters thing where they actually busted this thing, where they showed how it would actually work. Okay. So I have to pause my recording. All right. That experiment did not work. Okay. The way that it was initially designed. Could Lexus have pulled it off to make it work? Absolutely, they could have. Okay. All that had to happen was the car on the ground goes faster than 105 miles an hour. Okay. Which it was probably capable of doing. Okay. And so it would have made up that little bit of difference. Okay. The other thing was that falling car in the Mythbusters video was bobbing back and forth. Okay, so it was getting into an aerodynamic dimension and then being buffeted the other way. Okay, that could have interfered with how swiftly it fell. Its terminal velocity could have been higher. Okay, all of those things could have led to that. Okay, but again, it's something that if you understand physics, you understand how things fall, you understand projectiles, that ad has less of an impact on you. Okay, but for the average person, they watch that ad and they are completely impressed. Okay, because they don't think about, okay, how does that situation work? They just go, gravity, fast car, faster. Okay? Me buy car, fast car. Okay? Like that's, you get that instinct. Okay, so, is that all right with everybody there? Okay, so falling projectile, or falling object is the simplest of the projectiles. Okay? Now, like we said, on Earth, things fall at 9.81 meters per second squared, but not forever. Okay? They are going to hit terminal velocity. We're not going to deal with those situations. Okay? All of our situations are falling in the utopian physical world where there's no air resistance and they continue to accelerate at 9.81 meters per second squared for the entire flight. Okay? If that's true, okay, an object that goes off of a cliff, okay, follows a perfectly even arc. Okay, that goes down. An object that's thrown on the ground has a perfectly symmetrical projectile arc. In the real world, that's not how they go. Okay? In the real world, this arc is much steeper because air resistance in the horizontal dimension, okay, will slow the car in the horizontal dimension, okay, and okay, there's also going to be the terminal velocity part, okay, happening there. Okay, for an object that's projected at an angle, okay, most of the time that arc looks more like that. Okay, the horizontal air resistance starts to play a bigger factor, okay, slowing the object down, okay, in that dimension. Okay, if you've ever watched golf at all, you can tell it like when they hit a ball, okay, it always follows the end of the arc is always flatter, okay, or steeper, sorry, than the initial part. Okay, making sense there? All right. Now, we were talking about this the other day, okay? We were talking about making certain shots, okay, as a marksman, or if you're even using a bow and arrow, which is simpler, over shorter distances, easier to kind of see the effect of. But obviously, if you want to hit a target that's any distance away, you don't aim directly for the bullseye. You aim above. Yeah, you have to take into account gravity is going to pull the projectile down, the arrow, the bullet, whatever it is going to bring it back to Earth. Okay, and so you have to correct for that. You actually have to aim above the target. Now, we'll talk more about that on Monday, but I'm going to show you some of the other ones I have here. The vacuum chamber one.